Our first speaker is Elizabeth Newman. She is a postdoctor. Now she is a assistant professor in scientific computing from Emory University. The title of her presentation is Chain Like Variable Project, Efficient Training of Neural Networks with Variable Projection. Elizabeth, now it's your time. Please go ahead.
Thank you so much for the introduction. Let me just share my screen. And hopefully this works like it did before. So can we all see that screen? And yell if you can't see it. But thank you very much for the introduction. I'm very excited to be here to talk about our recent work. It's called Train Like a VarPro. This is a joint work with my advisor at Emory, Lars Ruthato, and our wonderful collaborators at Sandia National Laboratories, Joseph Hart and Bart van Bloemen-Wanders. So let's get started with a very shallow look at deep neural networks. And I'll start by saying breaking neural networks into these two big tasks that you sometimes see. The first one is classification, where you have, let's say, some image of a dog. This is my family dog's Honey, and we're trying to classify this image as a dog. So we put this image into a neural network, which we can visualize as a sequence of connected layers, and these connections are weighted, and we're trying to learn the weights that will give us this correct label. The other option is something like function approximation, where you have some true function, and as you train, your approximation from your neural network gets better and better, and the error goes down. There are many more tasks that you can do with neural networks, but these are the two broad ones that I want to focus on today. So the hype with neural networks, you've probably heard that they're universal approximators. They can be efficient surrogates, and they offer a flexible framework. But there are challenges associated with neural networks. They tend not to generalize well just if you train naively. They might overfit the training data. They're not interpretable. They're often this black box it's hard to understand. And training takes a long time. It can be incredibly inefficient. So we're going to focus on how we're going to improve the training in this talk. We're going to employ second order methods, try to introduce ways of potentially using more data parallelism. And kind of the heart of VarPro is we're going to find a way to choose optimal parameters as we train. So let's kind of let's talk about what does this mean, figuring out these optimal parameters. So in general, we have some set of inputs, Y. We want to find a DNN, a deep neural network, that maps to some true targets, C. And that's as abstract as I can make it. If you look at some of these state-of-the-art networks, they all look a little bit different. Their layers look different, but they have something in common. In particular, they have this separable structure. So their final layer can be written as just some matrix, some dense matrix applied to the outputs. So we're going to think about DNNs as having this separable structure. We're going to map from inputs to outputs with some nonlinear mapping F, parameterized by theta. So that's what we'll call the feature extractor, inputs to outputs. And then we'll separate this and have a final affine mapping, which I'll call a linear classifier. This doesn't have to be used for classification tasks only. It's just an easier way to talk about it. So with this separable structure, we can get a lot more bang for our buck by actually taking this into account. So let's do a quick kind of toy example to motivate why this is so powerful to think about this separable structure. Let's say we have some training data. So these are points on the plane, and they're classified as either the red or the blue class based on their distance from the origin. And if we run this through a neural network, the points, we can visualize them as moving in space. You'll see the points here. These are the dots here are the outputs Z. And our goal is to actually draw a line, a hyperplane between these two colors. That means we can classify them accurately. This black line is that line that classifies blue and red as the best it possibly can. And that's our W there. So getting the points into this new configuration, that's the feature extraction. And then drawing this line is the classification step. So there are two ways we can actually figure out this line. One is we can actually think about the W and the theta as being the same set, a big set of parameters in your network that you train with some network optimization strategy like stochastic gradient descent. So that's when we learn this W. The other way we can think about it is as we're training, why don't we just find the optimal W at each training epoch or iteration? And I'm going to give you two videos side by side to compare this. On the left, you're going to see the traditional treating W as a parameter that you learn. On the right, you're going to see what happens if we have W, choose it optimally at each training iteration. So let's see if this works. So you can see here, it looks really good in the optimal case. The red and the blue, we can divide them perfectly. In this learn W case, it actually didn't do a great job. It definitely separated the red and the blue, but it didn't learn as well nor as efficiently. So let me do it one more time, because look how quickly we can learn if we use the optimal W. Right about here, we already have a good classification. So this is kind of the main idea of VarPro is, can we accelerate learning and do it better by using this optimal linear transformation or affine mapping at the end. So to put a little notation to this, let's say we have some training data set T, and we have our network weights that we're learning both here, W and theta. We want to minimize this objective function phi, and that's a combination of some loss function that measures the approximation of the target to the true target. This is our separable structure that you saw before, and some regularization as well. The main idea of VarPro is to eliminate this W and exploit this inherent coupling between theta and W. And this should accelerate the convergence as we saw in the previous example. So this leads us to the reduced objective function, phi red, which is just the full objective function above, but evaluated at this specific choice of W theta. And this W theta comes from a bi-level optimization strategy where we actually minimize the full objective function with respect to W only. And that's it. That's the whole idea of VarPro. Now, there's an important consideration here that we recommend in our paper to use a sample average approximation when you're training, meaning use large batches as opposed to small batches you typically see in stochastic approximation. And this avoids overfitting when you solve this inner optimization problem. We're not saying one method is better than the other, but for VarPro, we recommend using this SAA method. So now, we can avoid overfitting, but there's actually, I want to show you why you're going to love VarPro and want to use it yourself. Because there's a really nice property between VarPro and not using VarPro. And that is that the gradient of the full objective function with respect to W evaluated at that optimal W is equal to 0. And that leads to this nice property that the gradient of the reduced objective function with respect to theta is equal to the gradient of the full objective function with respect to theta, again, evaluated at this optimal W. So this means whatever you have already to train your neural network, you can do this and you can still just use VarPro. You don't have to change your gradient calculations or anything as long as you just need these gradients. So it's actually not too difficult of a change to make. So let's, the key here is we have to make sure we solve this inner optimization problem well so that the gradient is close to 0. So that's what I'll talk about next. How do we solve this inner optimization problem? And for us, we're gonna, we first noticed some really nice properties about this inner optimization problem. It's modest in size. and does not depend on the DNN architecture, or really doesn't depend on the feature extractor at all. So it's something we can completely separate from the forward propagation through that nonlinear part of the network. The negatives or the challenges associated with this is that for a general choice of objective function phi that has these properties, there's no closed form solution. So we need some sort of iterative solver. And we want to make sure we can solve efficiently to a high accuracy. We want to reduce the overhead of using VarPro. So we're going to use a Newton-Krylov trust region method. That's what we've implemented, where you have your current iterate Wj, and you're trying to update it in the direction delta W, where you form this delta W by minimizing a quadratic approximation about your current iterate Wj. So this is our quadratic approximation. It's a trust region method. So at our current iterate, we can only take a step within a certain radius, within a certain ball. And when we do this, this would be our trust region step. It's minimizing the quadratic model, but stays within the radius. Compare that to, say, a line search method, which will minimize the quadratic model and then change the length of the step. And we're going to make better progress toward this kidney-shaped functions minimum right around here with the trust region method. So we like this. It's a more reliable method we found in practice. And additionally, there are other there's efficiency and accuracy we can add in here. When we minimize this quadratic model, we use a GMres approach, and so we get this low rank approximation to the Hessian. This approximation we can actually use later in our network. I won't be talking about that, but it's in our paper. But it's something that we don't need to store a lot, and we can reuse it. So you get a lot of bang for your buck here. Additionally, because the problem is modest in size and it's the final layer of your network, we can use double precision and detach, don't use automatic, and not use automatic differentiation. So you don't have to do these things, but it can really reduce the cost of using VarPro, and can give you all the benefits of using it as well. So this is the VarPro method, but we wanted to go a little further, and we were wondering, can we actually speed up training the network parameters theta as well? So we propose GNvpro, a Gauss-Newton-Krylov VarPro method. And here's just the reduced optimization problem as a reminder. The idea of GNvpro is that using a second order method, we can accelerate convergence and still achieve a high accuracy by having the VarPro in there. However, there's a challenge associated with this, where we have to implement Jacobians very carefully. So let's just compare it to what we saw before. Now we're updating theta instead of W, but we're using the same kind of trust region approach. The difference is the Hessian here, we're going to approximate by a Jacobian transposed Jacobian. And this Jacobian right here, with respect to W theta and F theta, so the affine mapping and the nonlinear mapping, has to be computed carefully. Both we require some implicit differentiation to capture this W theta accurately, and also it's expensive to go through the nonlinear feature extractor, and it's expensive to compute the Jacobian as well, which is going backward. It can be thought of as going backward through the feature extractor as well. So we want to reduce the number of times we have to do that. But yeah, once we have all of that machinery working, we now have a second order method to train networks. And I want to show you what you can get for this. So here's our first example. This is an image segmentation problem, where our goal is we have some image here, and we're trying to label each pixel. As in this Indian Pines example, each pixel corresponds to some material or crop from a bird's eye view of the Indian Pines area. The loss function we're using here is a cross entropy loss, so it's non-quadratic. There is no closed form solution, and so we really needed a reliable iterative solver, that trust region, Newton-Krylov trust region method, to use VarPro here. And this is something that is new in our paper. You don't see it, we haven't seen it yet for neural networks. So here are just some results by picture here. So here's the ground truth you just saw. In this first column, this is the full Gauss-Newton, no VarPro. And this is our prediction, and you can see the difference is probably more helpful. How we didn't do very well. We didn't get a lot of the pixels accurately classified. Here's an SGD approach without no VarPro again, because the batches are too small, but it does pretty well. And here are two VarPro approaches. Here's the GNvpro that I described before. And this these all do comparably well, but what's surprising is that GNvpro had the best test accuracy. So it actually generalized better than SGD for this experiment, which surprised us, but we were excited to hear that, or to see that. And we're not exactly sure why, but definitely using large batches helped. So we were able to train faster, and we were able to generalize it as well. And we want to explore this more. So I said we train faster. So I want to give you a different example to show you how quickly we can train. And here is a PDE surrogate modeling example where we have some PDE that's parameterized by Y, and we solve it and discretize it into some set of observable C. So again, we're always mapping Y to C in this notation. Our goal is to train this neural network as an efficient PDE, as an efficient mapping that avoids expensive PDE solves. Here we use a mean squared error, so we can actually use some old VarPro techniques to solve the inner optimization problem. But here's a plot of the convergence. So this is the loss, how well we fit the data. And you'll see with GNvpro, we get to a lower loss, actually 2 orders of magnitude lower than even SGD, and we do it faster. So this is something we're really excited to see: high accuracy, fast training, especially for these scientific applications where accuracy matters a lot. So to wrap it up, in our group, we like to jokingly call GNvpro the backslash of neural networks for those familiar with MATLAB. Again, I'm not saying it is or isn't, it's just a fun thing for us to say. We've seen it accelerates training of DNNs. We can apply to non-quadratic objective functions. It does not depend on that feature extractor. And because we're using SAA methods in Gauss-Newton, we can potentially parallelize this significantly. We want to apply GNvpro to more problems, image classification, other scientific applications, implemented in other frameworks like PyTorch. We're close to having that ready. And we want to see if we can extend this to a stochastic approximation scheme. And that's where we're headed. So thanks for listening. Please feel free to check out our paper and our code and become a DNN pro yourself. So thank you.
Thanks, Elizabeth. Thank you for your great talk. Catherine, is there any questions on Zoom?
There aren't any questions, but I have a question, if that's okay.
Yes.
I was wondering, maybe this is a bit general. Are you aware of how sensitive your method is to perturbations, say in the data or elsewhere throughout the algorithm?
We haven't actually looked at that yet, but that's a really good idea. I'll even write that down. It's a great idea.
Okay, cool.
Okay. Jemima, is there any questions on YouTube?
No, none on YouTube.
Okay. Thank you, Elizabeth. Thank you again.
Okay, I'll stop sharing. Thank you very much.
Yes.